So now let's look at the solution code from USICO's website. So this code are on 2 slides. This is in C++. So the global variables, there is this array of vectors. So here, instead of actually using a stack, so it's just done using a vector, which is perfectly fine, because the vector you can access at the end, which is essentially the same as a stack. And the code declares n stacks, but when we start, they are all empty. And n is the problem specification is we have up to 10 to the 5. So because array will start index at 0, and here we are doing it at 1. So here so this is something that's fairly common, I find, in code from competitive programmer, is you declare a constant which is maximum size plus 5. So this is I guess trying to deal with sometimes you need an extra element in the beginning, sometimes you need an extra element in the end. So this just makes sure there's enough. So not all the index will actually be used. So another thing that's fairly interesting in the code is they use this array base to identify for each element which stack it belongs to. So if I were to write this, I will probably use a map. Map each map each element to either to the stack or to the base element. And I will probably need to put all the base in some sorted data structure so that I can use binary search to find where it is. But this here the solution is more elegant. It uses an array to store the value of the base of the stack. So and then you can use this array to figure out which stack it goes to. So this is so given this input, in the end, this is what the base value will look like. So because the first thing we see is 4, we will put down 4. Then anything less than 4 will have to go on 4. So we will fill in the array all the way from here to here. So all the element 1, 2, 3, they will need to go to 4. So given a new element 2, we will look this up. We know, oh, 4 is the base. So then we just do this item 4 will be the stack corresponding to that. And the next one is 5. At that point, 5, this base array still started at 0. So then we know it has not been assigned a stack yet. So we'll put down 5 here. But the next one is already filled with value 4. It's already non-zero. So then we know only 5 should go in this stack. So the main part of the code is on the next slide, but here placed will remember the largest thing that I have already taken, and answer is the value that we are going to output, the length of the prefix, and we're just going to keep processing this thing one by one. So we read in the value x. So the first thing to check is whether x is less than the thing we have already taken. So in that case, we break. We're done. So we cannot go on further. So then, I guess here there's So then the answer is I. So starting from 0, we are treating the ith element, but which we cannot handle. So that means we've handled from 0 to i-1. There are I elements that have been handled. So then the next step is we check whether this need to start a new stack. This will become the base of a new stack. So what we do is we check whether this base j, so starting from x, we first check whether base x is 0. So if it's 0, that means we haven't seen anything this big yet. So then this will start a new stack. So x will start a new stack. So then base x will be assigned x, but base x minus 1 will also be assigned x, so long as it's not already assigned a value. So this is if we execute this on 4, this is where all these 4 values are filled. So when we see 4, when we start, all of these are 0. So we see 4 assigned here. Because all of these are 0, we will assign 4 all the way here. So this code also illustrates another concept in algorithm analysis, which is what's it called? So the amortized cost. So essentially, for each element, this thing may be executed up to O(n) times. Because if the first element we see is n, then this loop will actually go through all of them. However, then later we will never need to assign things again. We only check, look it up, and then we know it's already filled. We don't need to do anything. So because each element in the base array is going to be filled only once, so the amortized cost is still constant time for handling each element. So yeah, so this is setting up the base, and then the next thing is we check things on the stack that these x need to go. That's determined by base x. So items of base x, this is a stack that x need to go. So we need to make sure the last element here is greater than x. So while it's non-empty and it's less than x, we will need to take those things away. So another interesting thing here is the code actually doesn't fully simulate the action. So you actually don't need to explicitly take all the stacks before you, because technically this if you think of this as taking the top of the current stack that x need to go into to make sure you're making sure taking smaller ones so that x can go. In order to take that, you actually need to take everything come before you first. So if the question asks you to produce all the sequence, then you do actually need to go through those stacks. But the question doesn't ask you that. So the code here actually doesn't explicitly take those out. It just takes this. But when it takes something, it will compute this placed. So this place will remember the maximum value that has been taken. So there is a so then what happens if we get a new element that should go into one of the earlier stack instead of this one? That will be called here because that element must be less than place. Then we already know it cannot be handled. So essentially, the moment we start taking one stack, the basic assumption is everything before this stack are already also taken. But we don't need to explicitly do that because those stacks won't be touched anymore. Because the only time we need to access those stacks is we see an element that's smaller than the current stack. But since we already start taking things, those things cannot be handled anymore. So that's sort of a part that I think saving the code to make the code shorter. And yeah, after all of this done, we just add it to the stack. So that's all for this question.